today's lecture, we're going to look at logarithmic functions. We went over exponential before, and we saw how the exponential looked like, right? Exponential look like this, where unknown is on the top power, right? So y equals to a to the x exponents. Sometimes it's easy to tell what your exponent is going to be, but sometimes not. For example, let's say if we have 2 to the x exponent equals to 4. This is obvious what x is going to be. So 2 to the what exponent makes it 4, right? So we know this x is going to be 2. So x is going to be 2. So in that case, we don't need help. We don't need to convert exponentials to logarithm. So we don't need help of logarithmic functions. But what about if we have 2 to the x exponent is equals to 3, right? I know that x have to be between 1 and 2 because 2 to the first exponent is 2. 2 to the second exponent is 4. So in order to get between here, your x is going to be between 1 or 2, right? But we don't know exact. Something like this, if we can use logarithmic functions, we should be able to get exact values, okay? So that's how we're going to learn logarithmic in this chapter with exponentials. So if we have y equal a to the x exponents, if we wanted to change this exponential into the logarithmic functions, you're going to have log a. So the base of the exponents will be small base of the logarithms, and then solution of the exponent become the larger base of the logarithms, and your exponent itself, usually in exponential, this is what unknown, right? That's going to be solution of the logarithms. Small base is the base of the exponentials. Larger base will be the solution of the exponentials, and x is going to be exponents of the exponentials, right? So this is how we're going to change from exponential forms to the logarithmic form. And we will do a few examples so that we will know how to convert it. And this is example where if you have 2 to the x exponent equals to 3 as an exponential, and if we wanted to convert that into the logarithm, we will have log 2, 3 equals to x. You see this this base becomes smaller base of the logarithm. Solution will be the larger base. Exponent will be the solution of the logarithms, right? And there is a few other properties that you need to memorize in logarithmic functions. The first one is going to be when you have log b to the 1, this is going to be always equals to 0. So this 1, so larger base is 1, logarithm larger base is 1, it will be always 0. Why do you think that is? I'm going to show you why it is. If I change this to the exponentials, I will have b to the 0 exponent is equals to 1. That's why if you have 1 as the larger base, this have to be 0. Only time that you will get 1 to the any base is going to be when you have a 0 exponents, right? So just remember, whenever you see 1 as the larger base, your solution have to be 0. The other one is when small base, larger base is same, it means this is equals to 1. So I'm going to show you with exponentials too. B to the first exponent is equals to b, right? So only time Only time this b is going to be b is when you have first exponents, right? The third one is when you have b and b, so small base and larger base same, and have exponents to the larger base, that exponent will be the solutions. Okay, so if I change that into exponentials, it will be b to the x exponent is going to be equals to b to the x exponent. This is that right there. Small base, and then solution will be exponents, right? The other one is b to the log b. So when logarithm is on the exponent of b, and then small base and this base is the same value, then this is going to be equals to the larger base of the logarithm. So these 4, you need to kind of memorize them. And this 4 plus number 9 and 10 is what we're going to use it in section 3. From 5, 6, 7, 8, property 5, 6, 7, 8, we're going to use it in the later sections. So let's look at 9. Sometime you will have logarithm with no small base. It means whenever you don't see a small base, that means your small base is 10. It's like a square root. You know, square roots, you don't write 2 as an index. So that's the same reason we don't put 10 here. So if you have a log 10, sometimes people do not write them. So when you don't see the small base, it means they're talking about log 10. And when you have a log e, when small base is e, we use the natural logarithm ln, Ln. So when you say ln, it means your logarithm small base is e, right? So this is 2 concepts you need to remember. And we will come back. Well, let's just look at it for a few. We will look at this 4 in our next section, more detail. But if you have a multiplications, you can stretch this logarithm by using additions. We call that product properties. If you have a divisions on the larger base of the logarithm, we can stretch the logarithm using the subtractions. So multiplication become additions, division becomes subtractions. If we have exponents, we can always make a multiplication to the logarithms. We call that power properties. If we have log b to the x, so small base is b, larger base is x, then we can change the base into a and separate the larger base onto the numerator and smaller base into the denominator. So usually we use this if we wanted to use the calculator, because if you check the calculator have log 10 and natural logarithms. But if you have log 2, 3, right? If you have a logarithm of 2 as the small base, you do not see that in your calculator. So in that case, you can change to change your base so that you can use a calculator. That's something, again, this 4, we will go over them next sections. So right now, let's just use this 6, 1, 2, the property 1, 2, 3, 4, 9, and 10. That's the property we're going to use to see if we can do some of the example for it. First example we have, before we simplify it or finding values, we wanted to see if we can change one form to the other form. For example, example 1, if we have a logarithm, we should know how to convert it into exponentials, right? So let's see, this exponential, the logarithm to exponential, we will start with the small base. Small base become base of the exponential. Solution right here, will be your exponent. Larger base will be the solution of the exponent. So let me draw the arrow. So this 2 become the base, solution become exponents, and larger base become the solutions. That's how you're going to change. And once you change to exponent, it kind of makes sense. 2 to the 4th exponent, 2 to the 4th exponent is 16, right? So it makes sense. Let's look at the next one. What about this b logarithm? We wanted to change that to the exponential. So start with the smaller base, and solution become, which is negative 2, become your power should be equal to your larger base of the logarithm will be the solutions. And again, this makes sense. Negative 2 exponent is same as having a denominator with 2 0, right? Let's look at C. What about log 7 to the first equals 0? Log 7 1 equals 0. Converting into exponential, it means 7 to the 0 exponent will be 1. Again, that we know that's true, right? Any number to the 0 exponent is equals to 1. Let's look at the other one. Example 2. So this time we're going to go backward. If we have exponential, we should be able to transfer into logarithmic forms. So we have 3 to the 4th exponent equals 81. How can we change that into logarithmic? It will be log, base of exponent becomes small base, solution equal exponents, right? So the way that you're going to, you never deal with logarithm before, but basically what logarithm is asking, when you're reading this logarithm, it will say, log 3, 81 equals to 4. Means how many 3 do you need to have in order to make 81? How many 3 you need to multiply to become 81? Well, that's obvious. 3 to the 4th exponents makes 81, right? Let's try another one. This one, change to logarithmic, so it will be log 10. And that's going to be, how many zeros? 6 0? So log 10, 1 million equals 6. Or other way to put it, if you don't want it to write that large numbers, this is equals to 10 to the 6 exponents, right? Which is equals to 6. And this is also one of the property. When you have small base and larger base same, then your exponent will be the solutions, right? And this is how you're going to change your exponentials to logarithm. Let's look at another one. So changing to logarithmic, right? So it will be log 1/5. 5 is -1. Again, it's asking what power do you need to have 1/5 to become 5? So 1/5 to become 5, you need to flip this 1/5, right? So 1/5, if you flip 1/5, become 5 over 1. So what will be the power of flipping? That's -1, right? -1 powers. So that's how you're going to change exponentials to logarithms. Now let's see if we can evaluate. In order to evaluate, we need to remember those properties that we went over from the beginning of these sections, right? So let's look at the first one, log 4/16. So how many 4 do you need to become 16? How many times you need to multiply 4 in order to become 16 is the questions, right? So we know that's going to be 2, right? 4 times 4 is 16. So this is going to be equals to 2. But let's say you don't know or you didn't understand that. All you need to do is converting this into exponentials. And you can tell this is going to be, x have to be 2, right? Let's look at the next one. Because one of the property, and I know that this 8 right here, I can use 2 to rewrite 8. So if I wanted to rewrite this, I could say log 2 cube is 8, right? The reason I convert 8 into 2 cube is because if I have small base and larger base same, then exponent will be the solutions, right? Exponent will be the solution, which is 3. So use the logarithmic property to solve this problem, or you can convert this into exponentials. So 2 to the y exponents, 2 to the y exponents makes it 8. We know that 8 is same as 2 cube. So as long as you have a same base, we can drop the base and we will say x is equals to 3. So either way, you get 3 as the solutions. You can keep it as the logarithmic function and use the property of the logarithm to solve, or convert it into the exponentials and make it same base, drop the base, let the exponents equals to each other. X equals to 3 once you have the same base, right? Let's try another one. So this one, if I have log 1/2 2. 8, right? So again, this one I can change to exponentials. Let's try that. If I wanted to change this to exponentials, I will say 1/2 to the y exponents makes 8, right? And I wanted to make a same base, then I can drop the base, let the exponent equals to each other. So I will do this as 2 to the negative first exponent to the x, and then 8 is 2 cube, right? And this is same as 2 to the negative x exponent equals to 2 cube, where you can see that same base, so drop the base, and you will say negative x equals to 3. So x should be equals to negative 3, where your solution is going to be x equals to negative 3. So if you change logarithmic into the exponentials, then you should be able to solve that by making the same base. D, we have log 100,000. Log 100,000. This one I don't have base, and one of the method that I can use is converting into the exponentials, right? So if I don't see any small base, remember that's same as having a 10 there, right? So if I wanted to change this into the exponentials, it will be 10 to the x exponent equals to 100,000. And make it into the same base, and we know that 100,000, I should be able to rewrite this into 10 to the, how many zero? 5, so it will be 10 to the 5th exponent. Once we have a same base, this is the same base, then drop the base and let the exponent equals to each other, right? So x equal to 5. That's one way of doing it. You can also do this problem using the property, logarithmic property. We can make it small base, larger base, same using the exponentials. So when you have small base, larger base, same, your solution will be exponent of the larger base, right? So this, if this two number is same, right? What about e? We have log 0.001. So again, this is going to be same as log 10. And 0.001, you can rewrite this into 10 to the negative third power. So small base, larger base, same, 10, it means the exponent will be the solutions, right? Or you can even convert into the exponential, which is going to be 10 to the what exponents make 0.001. And then we know that's 10 to the negative third. So that gives you negative 3, right? Either way, again, using the property of the logarithm or converting into the exponentials will give you the same solution if the steps are all right. Okay. Let's look at f. What about if we have ln e to the 4th exponent? When I see ln functions, natural logarithm, we know that's going to be same as having log e, and then you have e to the 4th exponent. Again, do you see here same small and larger base? Whenever you have a same small and larger base, your exponent will be the solutions. So your solution will be 4. G, you have natural logarithm of 1 over e. We can change that into, again, log e to the 1 over e. And we know 1 over e is same as e to the negative 1 exponents. And here you have small base, larger base, same. So your solution should be larger base exponents. So it will be negative 1 for that problem. Let's do one more example. Example 4. If you want to, you can try them out first. We still going to use those property that we have. So let's look at this problem right here, because I see that small base right here is same as the larger base. So without double thinking, this exponent should be my solutions. So if you remember that property, that easy to solve that problems. What about B? This is going to be 2 also, but because natural logarithm is same as log e, and e to the e to the square, right? Again, small base, larger base, same, so exponent should be your solutions. This one right here, you have small base, larger base is same. What's the exponents of the larger base? You don't see any. It means you have 1, right? And that was one of other property too. If you have a small base and larger base same, no exponents, then 1 will be the solutions, right? D, this is going to be, again, 1. Why is that? Because we know this is log 10, 10, right? If you don't see small base, it means you have 10. Let's look at E. You have log square root of 7, 1. So we wanted to change this into exponentials. Then I have square root of 7 to the x exponent equals to 1. And your exponent have to be no matter what your base you have. I mean, this is square root of 7. So sometimes people look at it, I don't remember ever dealing with square root 7 on the base, but no matter what number base is, in order to get 1, your exponent have to be 0, right? So we know that x is going to be 0. Or if you remember from one of the property, when larger base is 1, your solution will be 0. For the same reason, f, this is going to be 0. Why? Because your larger base right here is 1. In order to get larger base 1, your exponent have to be 0. You can also convert this to log E1 and then equals to 0. G, we have exponent, logarithm on the exponent of 5. And we remember one of the property when the base and small base of the logarithm is the same, then larger base become your solutions. So this is going to be equal to a squared plus 4. So again, these two value have to be same. This value and this value should be the same. Then larger base of logarithm will be the solutions. H, I don't see the small base of the exponential logarithms. But if you don't see it, it means you have 10 there, right? You have 10. So now you have same value, 10 and 10. So your solution will be a squared plus b squared. So that's just, if you remember the property, you can just write down your solutions. Example 5, we wanted to graph logarithmic functions to show you the comparison with exponentials. And also, in example 5 graphing, I also wanted to show that you can use the transformations. So example 5a, we have y equals to log 2x. So we will start graphing by plugging the points. The easy number to pick x is going to be either 1 and 4, right? 4 or even 8 and all those numbers that exponent of 2. So let's try 4 and 1. So when x is 1, we know y have to be 0. When x is 4, we know y have to be 2. With that 2 points, I should be able to graph this logarithmic functions. When x is 1, y will be 0, so that will be this point it passed, right? And then when x is 4, 2, 3, 4, y will be 1. Y will be 2, right? So when you draw the line, and if you wanted to try how far it goes, right? How far we go, is it passing your y-axis, right? If you want to, you can plug in x equals to negative numbers. Can I put x equals to negative number here? Well, your x is larger base. That's one of the rules you have. The larger base cannot be negative because 2 to the any exponents will never become negative numbers. Remember from exponentials, right? So this larger base, you cannot have negative numbers. It means when you're graphing it, you need to make sure the line passing those 2 points will never cross y-axis. This x cannot be 0 right here, right? So another way to look at it, your vertical asymptote will be x equal 0. So vertical asymptote is x equals to 0. So then when you graph this, passing those 2 points with smooth curved line go toward your vertical asymptote but never pass, right? So this is the shape of the graph you're going to have for the log 2x. And remember, looking at from the previous section, remember looking at 2 to the x exponent equals to y before? When we graph that, we have graph look like this. So that we remember that logarithm and exponential is inverse. When we fold the line through, let's use the different colors. So when we fold the line through this green line, they are the graph from the logarithms and graph from exponentials. They are on top of each other, so they're mirroring each other's from this green lines, right? So we know this is inverse functions. Don't forget this one right here is exponentials. This one right here is the logarithm. Exponentials have horizontal asymptote. Logarithm have the vertical asymptotes. So that's the relationship of exponentials and logarithms. If I wanted to look at example B, graphing. As you can see, this is going to be same base. So y equals to log 2x, and I have y equals to log 2x plus 3 minus 2. So these two, a and b, are starting from the same base of the logarithm 2. Only thing that is added in b is plus 3 to the variable x and minus 2 to the whole functions of y, right? So this means if we wanted to use the transformations, this plus 3 right here will give you move left 3. And this 2, negative 2 will give you going down 2, right? From the same graph as the example A. From the example A graph, you're going to move left 3, going down 2. So moving left 3, your vertical asymptote is going to be moved left 3 also. It was x equals to 0. Now moving left 3, you will have negative 3. And draw the vertical asymptotes. Going down 3 will be still vertical line, so it's not going to be matter, right? And then where it was 0, 0, okay, so this point right here, remember this point when x is 1, y is 0, that point, you're going to go left 3, down 2. So from here, left 3 is going to be here, right? Left 3, down 2, 1, 2 will be that point. The same point, 4 and 2, you're going to move 3 left, down 2 will be this point right here, right? So from here, go left 3, 1, 2, 3, go down 2, 1, 2. So it will be the same point. So this is how it should be smooth curved line, right? Passing those 2 points, going toward your asymptote, but never pass, right? So that's going to be graph for B. This is 1, this is negative 2, right? And this is negative 2.